Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Scientists are inventing metals and ceramics and all sorts of new materials. Once they invent it, they need to understand it so that they know how to use it. This often means studying material toughness or flexibility and how these properties change if you deform the material. Ashley Busick is a mechanical engineer at the University of Michigan. She studies the mechanical properties of materials under stress. In her research, she uses a tool called a 3D X-ray diffraction microscope, or 3D XRD, to look at the small grains that make up the material. She wants to know how changes on the small scale lead to changes in the bulk.
You can measure the local deformation and then tie that together to try to understand how that sort of aggregates to the global or macroscopic deformation or mechanical properties.
In 3D XRD, you aim X-rays at a rotating sample to get images of it from different angles, which you then reconstruct into a 3D image. But this microscope needs a lot of X-rays, which has meant that these machines require specialized facilities known as synchrotrons. These are huge particle accelerators that produce X-rays at the volume needed to image these materials. You have to apply and be approved for time at the facility months in advance, and then you have limited time to take the data that you need. Busick wondered if she could make a 3D XRD without a synchrotron. She wanted to miniaturize this microscope.
I thought, well, if the sources are more powerful than they were 10 years ago, and detectors are obviously better than they were 10 years ago, maybe it's possible to do it at the lab scale.
Busick's team paired up with Proto Manufacturing, a Michigan-based company specializing in X-ray diffraction instruments. After about 3 years, including delays due to the COVID-19 pandemic, they successfully built a lab-scale 3D X-ray diffraction microscope. It costs on the order of $1 million to build.
If you walk into our lab, there's like a miniature room in the middle of the lab. So the machine is in that miniature room.
A key element of the design is the material they use to make the X-rays. Typically, you bombard a solid metal target with electrons to produce X-rays, but the metal would melt to produce the amount of X-rays needed for their machine. To circumvent the X-ray source melting, they use a liquid metal source to generate the X-rays, instead of a solid metal one.
Ours is indium, tin, and thallium. They add the thallium so that it is liquid at room temperature. And what that means is that we don't have to worry so much about throwing more power into the source, because if it gets so hot, it's just going to stay liquid.
This liquid metal source essentially serves the purpose of a synchrotron, which is to produce X-rays. Because they didn't need a synchrotron anymore, this allowed them to shrink the 3D XRD to fit in a lab. But in some circumstances, Busick says you might still need a synchrotron-based microscope.
Our microscope is like a really, really nice, expensive backyard telescope, where the synchrotron is more like the Hubble. So there are cases where you still want the Hubble and need the Hubble, but there are also cases where the Hubble is overkill, and you could just use your really nice backyard telescope.
In comparison with the synchrotron, their lab-based one is slower. It takes about 45 minutes per measurement, compared to 90 seconds at some synchrotrons. It has some other limitations as well.
The resolution in terms of strain and orientation are comparable to what we get at the synchrotron, but we can't measure small grains like you can at the synchrotron.
Right now, they are using the machine to study the mechanical properties of granular mixtures of silicon and ruby. The lab-based microscope also allows them to study these materials at different time scales than they could at the synchrotron. Typically, you get a few days to use the synchrotron and you have to move on. Here, they can be a lot more creative with time.
What if we vibrate this sample for 1 year? How does the topology of the crystal arrangement change? And so the time scales are really long, and the materials work really well with our microscope.
This work was published in a recent issue of Nature Communications. My name is Sophia Chen from the Materials Research Society. For more news, log onto the MRS Bulletin website at mrsbulletin.org and follow us on X @MRSBulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.